Hello, welcome back. I am Mr. Cobalt, and today I will be going over a problem where we're going to use partial pressures and mole fractions to solve a problem. So let's get into this. So it says you have a 12.5 liter scuba diving tank, and it contains helium oxygen heliox mixture made up of 24.2 grams of helium and 4.32 grams of oxygen at 298. It asks you to calculate the mole fraction, the partial pressure of each component in the mixture, and the total pressure of the mixture itself. So there's a lot to find out here. So let's start with calculating the mole fraction. If you remember, the mole fraction is basically calculated by the number of moles of your gas that you're interested in, one of the components of the gas divided by the total moles of the gas. So let's go ahead and do that. So what we have is mass. So they're giving us mass of the two components of the mixture. So we need to convert grams to moles. So we're going to use the molar mass to do that. So we're going to start with helium, 24.2 grams of the helium, and we're going to use the molar mass. Helium, that's going to be 4.00 grams of helium on the bottom to cancel out the grams, and we're going to have 1 mole of helium on top. So grams will cancel out, and that'll give us moles of helium. Then we do the same thing for oxygen. So we have 4.32 grams of O2, because oxygen is a diatomic molecule or element. And then, so the atomic mass of oxygen is 16, so multiply that by 2, it gives you 32. So 32.00 grams of oxygen on the bottom, and that gives you 1 mole of oxygen on the top. So again, grams of oxygen cancel out. Now you have moles. And so we're going to calculate the mole amount. So that's going to be 24.2 divided by 4.00 equals, and that's going to give us 6.05 moles. So we have 6.05 moles of the helium. And then we do the same thing for the oxygen. So we have 4.32 divided by 32.00 equals, so 0.135, 0.135, and that's O2. And so you'll notice that we have to watch our sig figs. So this is 3 sig figs, 3 sig figs. So our answer should be the least number of sig figs, which is 3. Here we have 3 sig figs, 4 sig figs. Least number is 3, so we should have 3, so that's good. So now we have the moles. So we just need the total moles, which is, add these together, and we get 6.185 total moles. So this is moles of oxygen, and so this is going to be total moles. All right, so now we have the total moles. We have the moles of each one. So now the mole fraction is just the moles of each component divided by the total. So, the mole fraction is this weird X called chi, Greek symbol. So that mole fraction of helium is going to be the moles of helium divided by the total moles, which is 6.185, 6.185. Now, when we added this together, we're only allowed the least number of decimal places. So we have 2 decimal places here, and we have 3 decimal places here because we added. So that means that this 8 is the last significant figure. But I'm going to keep the extra digit so that way I don't get a rounding error. So I should be aware of that. So that's going to give me the mole fraction for helium. So if I do 6.05 divided by 6.185 equals, and that gives me 0.97817, 0.97817, 79,817. So, and then this is uniless because this is moles total, and so moles cancel out, and so this is the mole fraction for helium. So again, because I'm dividing, I have to make sure that I have the right number of sig figs. So I should have the least number of sig figs in my answer. So I have 3 here because the 8 is the last one. I don't count the 5. So I have 3 here and I have 3 here. So the least number is 3. So the 8 is going to be the last one. I'm keeping the last 2 digits because I need to continue this with the calculation. So now I have the mole fraction of helium. So there's 2 ways I can find the mole fraction of oxygen. I can either take the mole fraction of the helium, subtract it from 1 because all mole fractions should add up to 1, or I can just do the same calculation. So we could just do the same calculation as we did here. So oxygen, so the moles of oxygen, 0.135 moles of oxygen over 6.185 moles total. And again, do the calculation. And so we have 0.135 divided by 6.185 equals, and I get 0.0218, and that's going to be the mole fraction. So moles cancel out. That's going to be the mole fraction of oxygen. If you add these together, you should get a number very, very close to 1. Alright, so now I have the mole fractions of each one. So they said find the mole fraction. Now we should find the partial pressures. Now we could find the partial pressure by using the ideal gas law. So we can use the ideal gas law to find the partial pressures because they gave us liters and they gave us temperature. And we found the moles, right? So we can use the moles, the temperature, and the liters, or the volume, to find the partial pressure of each gas. So we can do this. So we can start with helium. So we have, so the ideal gas law is PV equals nRT. We solve for, we want number of, what do we want? Pressure, partial pressure. So that means that the partial pressure of helium is going to be equal to the moles of helium. So the moles of helium multiplied by RT divided by P. So we just need to plug those values in. The moles of helium is 6.05 moles multiplied by R, 0.08206 liter atmospheres over mole Kelvin, multiplied by temperature, which is 298 Kelvin, 298 Kelvin, and then divided by the pressure, which is, not the pressure, that's the volume. Divided by the volume, which is 12.5 liters. So liters cancels out, moles cancels out, Kelvin cancels out, leaving atmospheres. And so we can go ahead and calculate that number. So we calculate it really quick. So 6.05 times 0.08206 times 298 divided by 12.5 equals, and that's going to give us 1183.56. 1183.56 atmospheres, right? And so figuring out the least, the sig figs. So remember, we have 3 here, we have 3 here, 4 here, 3 here. So the least number is 3, so that's going to be our last digit there. So now we can do the same thing for oxygen. So the partial pressure of oxygen is equal to the same thing. The moles of oxygen times RT divided by volume. So we use the moles, 0.135 moles of oxygen multiplied by 0.08206 liter atmospheres over mole Kelvin. And then we're going to multiply by the temperature to 98 Kelvin, and then we're going to divide by the same volume, 12.5 liters. So liters cancels out, Kelvin cancels out, moles cancels out, leaves us with atmospheres. So we do the calculation, and it should give us atmospheres. So let's do that quickly. 0.135 times 0.08206 times 298 divided by 12.5 equals, that's going to give us 0.264. That's going to equal 0.26410 atmospheres. So that's going to be the partial pressure of oxygen. So we have the partial pressure of oxygen, and we have the partial pressure of helium. And we got that from the ideal gas law. So now we can do this in a couple ways. The total pressure, which is what they're asking, should be the two added together. So we can add that together really quickly. So we add that plus 11.8356 equals, and so that gives us 12.0997. So that gives us 12.0997. Okay, let's check our sig figs. So this is 3, 3, 4, and 3, so we should have 3 there. If we add these together, least number of decimal places. So this is 1 decimal place. This is 3, so we are only allowed 1 decimal place. So we round that to a 1. So the total should be 12.1 atmospheres. Now, that's the first way we can do it. The second way is to use the equation that P, the pressure of one of the gases, the partial pressure is equal to the mole fraction of that gas times the total pressure. If we solve for total pressure divided by the mole fraction. So the total pressure should be equal to any of the partial pressures, the partial pressure of the substance divided by the mole fraction. So if we take that, so let's use the mole fraction of helium. So if we do the mole fraction of helium, then we can solve for the total pressure. So here, P total is going to be equal to the partial pressure of helium, which is, where is it? Going to be 11, so 11.83 atmospheres divided by mole fraction, which is going to be, where's the mole fraction? Just mole fraction. The mole fraction is 0.97817. So if we calculate that really quick, 11.83 divided by 0.97817 equals, and we get 12.09 right there. So, and then that's the same as the number we got before, right down here, 12 point rounded to 12.1. So both the methods work. I hope that was helpful. See you next time.